All right, everyone. Here is another topic that we best be really clear on. It's called present values of annuities. And this is for people who have been listening to me saying, Mr. Jennings, you've been talking about how great it is to take like $50 or $100 a month and start putting it away and putting it into interest earning investment opportunities. But I'm not in that boat. I want my money now, and I'm willing to pay for it later because I want that car now, or I want that sweet gaming console now because my YouTube channel is really going to take off and I'm going to be a big Twitch streamer. So I need to have the money now so I can do things in the future. Or maybe you're saying, well, I'm going to be borrowing money to go to school and I'm going to be making that investment in my future. So I can't be investing right now. In fact, I want a loan. Okay, so annuities can also work in reverse. You can get the money now and then you pay for it later. Of course, you end up paying more money the longer it takes you to pay because you pay more interest. But these work with similar mathematics, and we're covering that now. So this also applies if you say want to put away some money so that you can make regular withdrawals in the future. Let's say you win the lottery, $1 million, and you say, well, if I just take that $1 million, I could spend it all in a month, and that would be very sad. I'd much rather see if I can put that money somewhere and make a regular withdrawal every month so that I have some sweet money to spend. Okay, so you put the money into an investment and you spend it for, say, 40 years until it's down to zero. Interest helps you spend more money than $1 million. Those are all present values of annuities and different examples of this topic. So, this tells you how much you need to put away now or how much you could borrow now. It's also used for loans, mortgages, car payments, and money that has to be paid back. So you can remove equal payments at regular intervals in the future, say for retirement. How much money will I need at age 65 in order to make a $20,000 withdrawal every year to cover my living expenses? Um, you know, that would help you answer that question. Who'd use this math? All right, and here's the formula that we have for this. Of course, I've already copied the formulas for you here in our Start Here document. Here's the future value formula. Here's the present value formula. You can derive these using geometric series and sequences, but it's tricky. I understand it's tricky, so memorize the formulas too. Okay? And if we ever test this material, I'll give you have a formula sheet because they're all Googleable. You forget these, Google it, right? Also, you'll find that the general population is not as good at you as you are at doing mathematics. In fact, one time I was teaching grade 11 university math at a private school, and right at the end of the semester, we were doing this topic, and they hired a PhD in mathematics. And they said, "Okay, Mr. Jennings, you've got a master's in English and like a minor in math at a university. So you just focus on your English classes. We'll get this PhD in mathematics teach the course." And we were looking at this topic, and she came in and she said, "Oh, you need to evaluate each term separately and then add them all up." I'm like, "Oh, it's a geometric sequence. It's a geometric series, and we have a formula for that. It's much easier to do it this way." So if she has problems, you can be darn well sure that the general population has problems with this. So you'll find if you go online and you say annuity calculator, you go on here, you'll find lots of different calculators that are online that allow you to input your I, your R's, your N's, and it just does it for you. Okay? So they exist, but you want to know how to use the formulas. So here we go. This is our formula. And just to recap, where to put my stylus? There it is. Okay, R. This is the regular payment. This is the regular raiment. No, this is the regular payment. The present value refers to how much you need to pay now in order to withdraw this money regularly, or how much you are loaned now, and then you have to pay this money back regularly. Okay, so this is money now. Okay, I is the amount of interest per compounding period. And then n, you see we have a negative exponent here. Aren't you glad that we learned about that? The negative n here is the number of payments or the number of compounding periods. And again, we calculate I. I is the annual interest rate, little r. That's not an n, that's a little r. Oh, so gross. This is a little r divided by the compounding periods there, see? And n is equal to the number of compounding periods times the time in years. Okay, so again, these little micro formulas show up again to find these two numbers. Okay, let's keep going. So how much money should be invested now? Compounded semi-annually. So semi-annually means twice a year. So here our C equals 2, and we want to know how much money. So that means present value equals question mark. How much money should be invested now? Now, present value. Compounded semi-annually at 4% per annum. Okay. So whoever put these problems together chooses boring interest rates that are still solid. This is a solid interest rate, but a little boring. 12% is not solid. It's hard to find. It might be exposed to some risk, but it's a little more exciting. And that's how I like to roll. Okay, 4% per annum. So this is now our I is equal to 4% divided by C, which is 2, equals 0.02. Okay. So that 3,000 can be withdrawn every 6 months for 5 years. So that's like, you want some money to fund your sports. So this could do your your summer, I don't know, maybe that's your sailing fees or something, or to maintain your sailboat. And then in the winter, that can be all of the amount of money that you need to spend to do hockey or something like that. So how much do you need now to cover that for 5 years? Okay, so T is 5. And so then our N would be equal to T times C. C is 2, so N is 10. Okay, N is equal to 10. $3,000, that's R, equals 3,000. All right, so let's use our formula. And just to remind you, the formula is R times 1 minus 1 plus I to the negative N, all divided by I. So let's write out that formula. Present value equals R times 1 minus 1 plus I to the negative N, all divided by I. And then always double check your formulas. Hooray, I got it correct. And now substitute in. So the present value, the amount that you would need to invest now in order to have $3,000 every 6 months for 5 years, is equal to $3,000 multiplied by 1 minus 1.02, because that's 1 plus this number, raised to the power negative 10, because we had n is 10, 5 years, but we do this 2 times a year, so 10, n bracket, all divided by 0.02. Okay, let's do it. Plug it and chug it. Okay, I'm going to put that there. Now, clear everything. 3,000. Good morning, Miles.
Can you have a warm bubba?
Oh, a warm bubba? Yeah, I'll get that for you in just a moment. So there is the number that we are going to divide by 0.02. You'll say, that's not a lot of money that I need to put away now. Yeah, I need to divide it by a very small number. Divide by 0.02 equals, there we go. So you need to put away right now $27,000 in order to withdraw $3,000 10 times. And so that's $30,000 that you're drawing out of this. And so you'll notice that this number is a little lower than $30,000. And that's the function of the interest that you're earning over the process of doing exactly this. of making these regular payments and having them earning interest going forward. So let's write that down, 26,947.77. 26 comma 9, what was it? 947. 948, we'll round up. We'll have a little bit more money left over in this account at the end. So therefore, $27,000 is required to make semi-annual withdrawals for 5 years to make $3,000 semi-annual withdrawals. Yeah, for 5 years there. So that's pretty cool, eh? You can put up some big change now and draw out a little bit more change over the time of that investment. This might be more applicable to a situation where it's like when you are planning your estate and you have some grandchildren and you want those grandchildren to remember you forever. You can say, well, I have saved $1 million in my lifetime, and I'm going to take that $1 million and give my grandchild $1,000 a month for 40 years or something like that, and they will be ever so thankful every month when that check comes in, right? They might be more thankful about $1 million check, but that thankfulness is going to fade over time. This is a way to prolong their thankfulness. All right. So Kareem, here he is deciding to purchase a used car for $7,500. He has to repay the loan at 4.5% compounded monthly. So we know that his present value.
Are they sausage or hot dogs?
Those are hot dogs. They need to be cooked. Leave them alone. $7,500. Okay. Is it? Oh. Can you get out of the fridge? Did you drop the milk or just drop the tray?
Tray.
Just put the tray on the counter. I'll fix it later. And close the fridge if you can. Equals the regular payment. So we want to know what's going to be the loan payment, okay? He plans on paying off the loan in 3 years. He's trying to what is his monthly payment. This is the first thing we want to find. So this is saying R equals what? Okay, we don't know. We're going to find it out. How much interest will he be paying in total by the end of the loan? Well, that we're going to have to figure that out as well. Oh, man. Okay, so R multiplied by 1 minus 1 plus I to the negative n, all divided by I, okay? And we can use that same trick again to take this, multiply by the reciprocal, and flip it over there. So this is what I'm going to plug on my calculator, but let's get our i's and our n's first. I is equal to 4.5 compounded monthly. So compounded monthly tells me C equals 12. So I is going to be 4.5% divided by 12 equals, it's not a repeating decimal, which is nice because 4.5 has a factor 0.3. Okay, so clear everything. 4.5 divided by 12 equals 0.375. All right, n is equal to 12 times how many years? 3 years. 3 is equal to 36. Okay, so there's our numbers. All right, I'm going to just rewrite this formula first, and I'm going to write it over here, so it's going to be I'm going to have lots of space. I multiplied by 7500. It was on the bottom over here, so that's going to come up to the top when I multiply both sides by I, and then I divide both sides by all that junk. Okay, 1 minus 1 plus I to the negative n. Okay, some of you might be saying, well, this is a negative exponent. Why don't I flip that up to the top? I have to subtract 1 from it, so it doesn't come up to the top in that way. Okay, we can't do that because it's connected to this not by multiplication but by subtraction. So I can't just write this on the top with a positive exponent. Not allowed. Don't do that. Okay, and there's no way to factor it nicely so that it comes up to the top. If it was possible, the formula would be written in a different way. Okay, so this is the simplest way, and this is equal to R. Okay, we've moved all that junk away. So let's substitute in our numbers. I'm going to do this in another color just to keep it a little clearer. Okay. I was equal to 0.375 multiplied by 7500. And then I'm going to divide that by 1 minus 1.375. This has an extra 0 in it, Mr. Jennings. Yes, thank you very much. Yes, it does. Oh, dear. This has 2 extra zeros in it because this is not a decimal. This is a percentage. Oh, yo, good thing I know how to self-check my work, right? Yeah, I'm looking at that number and I'm like, that number ain't right. So I'm just going to put a big decimal there. Try and erase that decimal. No, missed it. Okay. There we go. All is forgiven. All is correct. Oh, no, not down there. I need to correct it too. Always be looking at your numbers and say, does that look reasonable? And then when you're like, no, then fix it before you plug it on a calculator. This is raised to the power negative 36. Okay, so that's going to be equal to R. All right, now let's plug that on the calculator. Clear everything. Move the calculator out of my own way. Okay, 0.00375 multiplied by 7,500 equals that amount of money on the top, divided by, put the bottom in brackets, 1 minus 1.00375 raised to the power negative 36. End bracket equals $223.10. So that's how much his monthly payment is. Okay, let's see if that feels reasonable. A car payment of $200 a month. Anyone buy a car yet, or anyone paying that kind of thing per month? Yeah. So that's what he's going to pay the $7,500 over 3 years. Now, 3 years is a short time frame to pay down a car. Some people will take longer, maybe 8 years. And also, people will pay down payments as well. So this is a very simplified situation. If he paid a down payment of $2,000, then we would say he pays $2,000 plus. Then we would have $5,500 in here in our equation, and it would have lowered the payment by a proportional amount. Okay. So anyway, that's how much he pays his monthly payment. Now, how much interest will he have paid in total by the end of the loan? Let's find that out. And to do that, we need to find what are his total payments. So we know that he makes 36 payments because he's paying monthly payments for 3 years. So that's 12 times 3 is 36. So if I take this number, R, which is big R, which is 22.3.10. Just make sure if I wrote that down right. Yeah, I did. Good for you, Mr. Jennings. Multiplied by 36. This is his total payments. So let's find out what that is. Times 36 equals, he pays a little over $8,000. $8,032. I'm going to round to the nearest dollar. This is $8,032. Erase this weird looking zero and write a proper looking zero. There we go. So that's how much he pays. And then, so therefore, he pays $532 in interest. Because to find out the interest, I say, how much did he pay overall? With a zero in there, for some reason, I'm not writing it down. And then I subtract the amount that he borrowed. If he just paid cash, that's what he would have paid, right? But for the privilege of being able to pay for it monthly over the course of 3 years, he paid $532 for that privilege. Okay, so the person who sold him this car, or the car dealership that sold him this car, made an extra $532 off of Kareem because Kareem did not want to pay cash. He wanted to pay that over a period of time. Now, he's only paying 4.5%. So that's a decent interest rate to have on a loan. Credit cards. Do people know what credit cards interest rates look like? Who can shout one out in the chat? Yeah, we have some assigned problems there. No one knows what a credit card interest rate might look like? Could be 20. Go ahead.
Aren't they over like 7% or something?
Oh, yeah, they're plenty over 7%. I think they're capped. I think that the legal limit, you cannot offer the consumer a credit card with a higher interest rate than 20%. Okay, so banks and credit loaning companies are making a ton of money out of that 20% interest. Okay. Now, that's the lesson for today, but I want to now just go to Desmos and show you 20% interest. Okay, we know that this is geometric. All right, this is the last little demo that I'm going to do. I'm going to compare 2% interest, which is what many people are paying, around 2% interest on their homes. 2% interest is like your mortgage payment. So let's say we have $1,000 and we're going to go 1.02. Okay, so this is 2%, and we're going to raise that to the power time. Okay, and now let's say, what's a reasonable scale? We want to look at, like, let's say over how many years? 60 years? 40 years? Let's do 40 years. Okay, what's a reasonable scale that I should look at to see how much money this is going to grow to after 40 years? This is not regular payments or anything. This is one. You borrow $1,000 and then you pay 2% interest on it for 40 years. Let's say, well, I don't know, what, like 10,000? Oh, there's 1,000, there's 10,000, and I can see it doesn't even touch. It doesn't get anywhere close to 10,000. It does not grow by 10 times. All right, let's change that to a 20% interest and see if we can still see this $1,000. Oh, no, we can't see the $1,000 anymore. It's gone off the scale. What scale should we use, everyone? What number should we see? It's way more than $10,000 after 40 years. Let's add a zero, see if we can see it. Let's see, does it grow to 100,000? No, it's still leaving the scale, Mr. Jennings, and its slope is still increasing. Well, let's look at $1,000,000. We should be able to see it, right? No, Mr. Jennings, it's still leaving the graph before 40 years, but we're close now. But I'm a little worried because its slope is still increasing. Okay, let's look at 10 million. We should surely be able to see it, right? Okay, yeah, we can see it now. Okay, so let's see. When x equals 40, what is it? It's going to be, notice that the Desmos has given up. And it's like, I'm just going to show you in scientific notation now because this is too big. Okay, so after 40 years, that credit card is now $1.4 million. $1,000 grows to $1.4 million with credit card interest rates. And I just want to remind you, this is the difference between a mortgage of 2%. Look, you can't see any growth here. That grew to $2,000. It doubled in 4 years at 2% interest. Okay, there. It, like, how much growth is that? It's more than it's 1,400 times growth. 1,400 times your money goes at a credit card. So when people tell you don't leave money on your credit card,
Mr.
don't leave
Jennings,
money on your credit card. Pay it off.
we can't really see anything on Desmos.
No? Why not?
Yeah, it looks like it's frozen or something.
My screen is frozen or something?
Yeah, because we can hear you talking and see you moving and stuff, but the actual website's not working.
Oh, weird. Okay. How about now? Can you see it here?
Yep.
Like this is your money growing, right? And I just have a $10 million scale here, but I don't need quite $10 million. So let's change that to a 2 there. And so then this is the money growing at 20% interest. That's $1,000, and you can't see any growth, right? But I promise you, its scale is constantly, its slope is constantly increasing. After 40 years, it became $1,469,771. So if you say, like, bought a flat screen TV, put it on your credit card, and then somehow forgot about that until you were 56 years old, you would owe the credit card company $1,400,069 and seven. You would owe them $1.5 million after 40 years for that $1,000, for the privilege of having $1,000 now. Okay, 20% interest is stupid. I mean, by stupid, I mean it's stupid huge. 2% interest is just massively different. Look at that; it's just a flat line, right? I need to really wind down the scale here. This is $2,200. So what I'm saying is 2% interest over 40 years it a little more than doubles. Okay, that's a mortgage rate level of interest. Okay, with 20% interest, just 10 times the interest, folks. Okay, the money grew by 1,400 times. That $1,000 became $1,400,000. Okay, so when people tell you don't leave money on a credit card and just say I'll pay it later, yes, don't leave money on a credit card ever. Like, always find another way to borrow the money and pay it down. Okay, always zero your credit card balance. Avoid leaving money on a credit card if at all possible. And it's like something that's just so important that you should be talking to loved ones about this as well. And if you can give them a mathematical argument, so much the better. Okay, so because I care about your mathematical progress, but I also care about you as human beings. I don't want you paying massive amounts of credit card interest over your lifetimes. So just, I hope that the difference between 20%, a growth factor of 1.2, and a growth factor of 1.02, I hope you can see it's not just 10 times worse. It can be like thousands of times worse, okay, if you let that compound because of the power of exponential growth. All right, everyone, so that's it for today. Thank you very much for showing up for your learning. Any questions before we wrap up the video? All right, great. Well, I wish you a fruitful math practice today. Any questions, come back to the chat. And don't run away right away because I want to get my screenshots of who's here. And any questions, you can also hit me up by email. Thanks very much, everyone. And